Let's dive right into the fascinating world of engineering materials. Welcome to today's Explainer, where we're going to look at the very building blocks of our modern world. You know, if you've ever felt completely overwhelmed by the sheer number of metals, alloys, and composites out there, well, you're absolutely in the right place. Today, we're giving you the professional memorization tips you need to master them. We're going to take this massive, complex web of information and turn it into a neatly organized mental filing cabinet. So, to kick things off, why don't we build airplanes out of solid steel or, I don't know, engine blocks out of wood? I mean, it sounds totally absurd, right? But what's really interesting about this question is how perfectly it highlights our fundamental need for diverse engineering materials. We have to maximize serviceability for highly specific applications. We don't just pick these materials at random. An engineer's primary goal is to keep all those negative factors to an absolute minimum, while pushing the positive factors, things like raw strength, heat resistance, or extreme lightness, to the absolute highest degree possible. Now, to really understand how we select these materials, we have to draw a hard line between two totally different concepts. On one side, we have fixed physical constants. These are basically the standardized numbers you'd look up in a handbook, like density or thermal conductivity. You can't really change them. But on the other side, we have engineering properties. These are the dynamic characteristics that we can actually manipulate. We tune them to our exact needs through processes like alloying, mechanical working, and heat treatment. And honestly, as professionals, this is where the real magic happens. Here is our roadmap for today. We're covering 1. The FNN framework, 2. Ferrous metals, 3. Non-ferrous metals, and finally 4. The 5 non-metallics. Section 1. The SNN framework, your mental filing cabinet. Okay, so the absolutely crucial takeaway here is that whenever you look at a material, whether that's a massive bridge girder or just a plastic cup on your desk, you should immediately drop it into one of 3 FNN folders: ferrous, non-ferrous, or non-metallic. This right here is the absolute bedrock of engineering metallurgy, because instead of trying to memorize thousands of individual unique materials, you literally just categorize them into these 3 broad, incredibly useful families. Now, this historically rigorous approach brilliantly illustrates that the structured analysis of these materials isn't new. It is a very well-established science. Historical texts on metallurgical analysis actually remind us that professionals have relied on this exact structured classification for decades. These testing and classification methods have been standardized by organizations globally. Why? To ensure that when an engineer designs a critical structure, they can trust with absolute certainty that the materials are going to behave exactly as predicted. Moving right along to Section 2. Ferrous metals, the heavyweights. So when we talk about ferrous metals, we are primarily talking about steel and cast iron. And, when tuning the engineering properties of steel, steelmen act a whole lot like professional chefs. They don't just randomly throw ingredients into a pot. Instead, they categorize any added alloying elements into 3 strict classes: harmful, beneficial, and neutral. By meticulously controlling these specific elements, they can eliminate excessive inclusions and manipulate the steel to hit that exact, perfect balance of strength and durability for whatever the job is. The sheer versatility of this first folder is staggering. I mean, applications range from the incredibly heavy, unalloyed steel castings required for massive steam and water lines, all the way down to highly specialized high nickel and chromium alloys. Just think about the heating elements in your everyday domestic appliances. Those are carefully engineered ferrous alloys, specifically designed to resist intense heat and conduct electricity efficiently. Without these specialized ferrous alloys, basic, everyday infrastructure like steam lines simply couldn't exist. And honestly, our buildings wouldn't even be habitable. Next up, Section 3. Non-ferrous metals, the special forces. Let's think about a really critical physical constant for a second: density. Magnesium holds this totally unique position of having the absolute lowest density among structural metals. It is far lower than aluminum and literally just a mere fraction of steel. So when the strength-to-weight ratio is your absolute highest priority, like say when you are trying to make a giant machine actually fly through the air, this physical constant dictates that you must open your non-ferrous folder and pull out magnesium or aluminum. These non-ferrous metals are totally indispensable when we need highly targeted solutions. Whether we need lightweight parts for aircraft construction using magnesium, highly corrosion-resistant anodized aluminum for rivets, or even utilizing the really specific low melting point properties of lead and tin alloys to make emergency safety plugs and compressed gas cylinders. The point is, each of these non-ferrous metals has a totally unique, predictable behavior that solves a very distinct engineering hurdle. And finally, Section 4, the 5 non-metallics, the rule of 5.
Okay, here is your rule of 5. I want you to lock this mental checklist in your head right now. Ready? Step 1, carbon and graphite. Step 2, ceramics, which includes things like glass and brick. Step 3, plastics, like nylon and vinyl. Step 4, rubbers, both the natural and synthetic kinds. And finally, step 5, wood. Those 5 classes completely round out your material taxonomy. Basically, if it's not iron-based and it's not another type of metal, it is going to fall into one of these 5 non-metallic categories.
But why do engineers actually rely on this third folder? Well, often it really comes down to survivability in incredibly harsh environments. These nonmetallics are frequently deployed for integral monolithic construction or as super thick sheet linings to solve severe corrosion problems. Think about chemical plants or highly corrosive settings where cheaper materials like standard steel would just rapidly degrade and fail. A thick lining of synthetic rubber or specific plastics, however, totally stands up to the challenge. It really proves that sometimes the absolute best engineering material isn't a metal at all.
As we wrap up this explainer, I want you to really consider this profound quote. Each class of carbon steel is indispensable, and the cost or tonnage is no criterion of its value to man. That actually perfectly summarizes our entire journey today. Whether we're talking about a cheap, heavy steel casting for an underground water pipe, an extremely expensive ultralight magnesium alloy for an airplane, or a highly specialized plastic lining, every single material in our FNN framework has been perfectly tuned for its specific engineering need, because true value isn't just about the cost, it's about achieving perfect serviceability.
So here is my personal challenge to you to help solidify all this new knowledge. Take a second and just look around the room you are in right now. Pick 5 random objects. Can you classify every single one of them using the FNN framework? Is that desk leg ferrous? Is your phone case in non-metallic plastic from our rule of 5? Put your new professional memorization tools to the test today, and I promise you will start seeing the entire engineered world through a fascinating new lens. Thank you so much for joining me on this explainer, and keep questioning what your world is really made of.